So this is where the Higgs comes into the story. Because going back to 1963, although it wasn't his prime motivation, Peter Higgs made a potentially extremely important contribution to cosmology because he talked about a vacuum density from the Higgs field, which we symbolize by phi. Now, nobody knows what the Higgs field is. It's just a thing that fills all of space. It's what we call a scalar field. It just means it's characterized by the value of one number, presumably the same number pretty well everywhere in space. And it's distinct from the electromagnetic field, which is a direction at every point in space. We don't know what the electromagnetic field is either, so physics is full of these things. We just accept that they exist. But what Peter added was that there was an energy density, which is normally written as V for potential, which was a function of the field. And as we've seen, that looked something like this. And what we think of as the Higgs boson are field oscillations down at the bottom of that potential. So from a cosmologist's point of view, the real significance of the detection of the Higgs is that it proved that the energy density of the vacuum is dynamical. That is, we know it's something that's capable of changing with time. So if the scalar field is here, potential is high. If the scalar field is here, the potential is low. And it's this ability of the energy density of the vacuum to change with time that's really critical for understanding the earliest phases of cosmology. So this idea of a vacuum density that could change with time was seized upon at the beginning of the 1980s by an American physicist, Alan Guth, where he invented a thing he called the inflationary universe. And the idea was very simple. He was thinking about how the universe would be at the grand unified theory era. This is a region of particle physics way beyond accelerators. Its energy, something like 10 to the 15 GeV. And he was thinking about the existence of fields like the Higgs field at that time and realizing that they might be able to dominate. If they did, the energy density would be something like 10 to the 80 kilograms per cubic meter, which is around over 100 powers of 10 different from the value that we actually measure today. So this is really, really large. And this gave him the very exciting idea that he could take an extremely small piece of space in a universe at this time. It would be only about 10 to the minus 26 meters across, subnuclear. This size is just the speed of light times the time at that particular energy. But if the vacuum can dominate, then this bubble starts to get bigger. And it grows exponentially huge. So this is scaled up maybe by e to the 60 powers of e at least. If you allow that to happen, you have an astonishing conclusion that this whole bubble is now potentially much larger than the visible universe. So the picture should be that within this, there's a little domain, and this is of size 14 times 10 to the 9 light years. And that's the part of this bubble that we can see. So our entire visible universe could be within a much larger inflationary bubble, as it's called. And think what's happened. It's this whole bubble is expanding. That expansion has been driven by the fact that early on the vacuum density had this huge value. Right, so now we can apply this to rewrite our suggestion for the expansion history of the universe. Once again, we had size versus time. The picture I showed you before was the Big Bang merging, decelerating, accelerating as dark energy gets a grip. But now what we're saying is that very close to early times, the vacuum energy was suddenly much larger than it is through all this period. And the result is it doesn't follow this trajectory at all. It's actually this. So here is Guth's inflation. The expansion of the universe is driven by the energy density of the vacuum. About here, the energy density of the vacuum falls to its present very low value. So here it's 10 to the 80. Here it's 10 to the minus 26. And the universe switches over to what looks like a Big Bang universe. And we think that it came from this singularity here. But actually, that's an incorrect extrapolation. We didn't allow for the fact that the vacuum energy could change. And if you allow for that, then actually there was no Big Bang at all. In some sense, it's just an illusion. The inflationary universe then allows us to understand how the universe got expanding in the first place, how it could become so large and uniform, how we could just live and be able to observe a very small domain within some much larger whole. But we wouldn't be here if the density of the universe was completely uniform. So there has to be structure within it. And amazingly, this same idea automatically generates that. Because as we've seen, this inflationary bubble, which is much larger than the invisible universe, started life on a tiny scale, subnuclear. So on those scales, we know that quantum mechanics dominates. So the idea that you could take a little piece of such a universe and have the density inside it uniform is completely impossible. There have to be small irregularities, and you can calculate them. And once they're present from quantum fluctuations, then gravity will get to grips. Wherever the density of matter is higher, matter gets sucked in at the expense of regions where the density of matter is less. And so eventually, this whole process terminates in real astronomical structures around us, such as the galaxies. And when we look around us, we see these complex structures, galaxies, objects of incredible beauty, all of which could have arisen from that simple piece of quantum mechanics. And if we look on a larger scale at a map of the distribution of the galaxies in space, we can see patterns in them that are hundreds or billions of light years across. And these, as far as we can tell, are the residue of these amplified quantum fluctuations that existed in a time when the vacuum energy was much larger than today. What is this scalar field whose associated vacuum density is going to have driven inflation? It's not the Higgs field. We know that because it would give the wrong amplitude of density fluctuations in the universe. So it has to be something else. A new field whose corresponding particle interacts very weakly, so that we haven't seen it so far. Most people aren't worried by that. There are many fields in nature, many particles that interact extremely weakly. It doesn't seem too bad to have one extra for the cosmological payback that it gives you. The trouble is, now you have no idea what its potential function is. It could be anything at all. So all we know is that the potential as a function of the scalar field has to have some point somewhere where it's very high, and eventually it has to find its way to a minimum, slightly offset from 0, and this is our observed present-day vacuum energy. So the universe at early times was here, and now it sits here. So doing a lot of cosmology comes down to thinking about different forms for this function and exploring their consequences. Yeah. So the picture that I just drew leaves a lot of people feeling deeply uneasy. We started off with a vacuum density of some huge value. This has eventually gone down to the observed really tiny value. And this is a puzzle because the vacuum density today is a combination of many different contributions. It's the 0-point fluctuations I talked about, plus the scalar field potential, and there could be many such contributions. And somehow they all to 0, but not quite 0, some very small residual number. It sounds like there's a conspiracy between all these contributions. How can that be? Well, there is one suggestion for solving this, and as far as I know, the only one that works. Which is to say that rather than living in a universe, we live in a multiverse. So to see how this could work, let's imagine a more complicated potential, one with lots of different minima. And imagine that each of these minima corresponded to a different inflationary bubble. So this would be one universe. It has a high vacuum density. So does this. So does this. These extremely high vacuum densities that we've seen will be incompatible with life. It's only a very rare minimum in this potential that might, just by luck, have a low enough value that life could exist. And therefore, it wouldn't be surprising that observers like us look around the universe, we find ourselves here. So this is an astonishing conclusion. We've known for about 100 years from astronomical observations that the patch of space that we inhabit, the matter in it is moving apart, expanding. We've gone from that simple observation to suggesting that maybe in an infinity of different universes out there with different laws of physics, we're lucky enough just to live in the one that is possible to contain life.